So what we want to do here, this town hall meeting, is to inform everybody about the advanced photon source upgrade, APSU, and how that's going to affect operations at the BioCAT facility in the upcoming year. So there's a couple of people that may not be that familiar with us. And so to remind you, here's the APS. It's in Argonne National Lab. It's a large physics accelerator, about 1 kilometer in circumference. The BioCAT facility is this one of these little triangular things outside is our sector. And we're exact opposite the main building, as I like to joke, is a safe distance from those guys. So what are we? We are a beamline, 18ID, and we provide scientific staff support. We have wet laboratory facilities and computational facilities. We have our operating budget's about $1 million a year. We have 3 scientific staff, a software engineer, 2 technical staff, and 1 administrator. What's a little bit confusing, we have no formal affiliation of Argonne National Lab. We're owned and operated by the Illinois Institute of Technology. We are funded by a P41 BTR grant from NIH since 1995 and by a P30 mechanism since 2021. We're part of the Center for Synchrotron Radiation Research and Instrumentation at IIT, and we're Pritzker Institute of Biomedical Science and Engineering. So what do we do? We're probably best known for our fiber diffraction activities. We've been doing muscle diffraction since the beginning, and our interests the applications tend to involve either muscle regulation, which is a big thing these days, heart disease, muscular dystrophy, and other skeletal muscle diseases. It's been the applications is expanding rapidly, and we're getting more involved in preclinical applications. Another traditional strength, which is a very small part of our program at the moment, is fiber crystallography, where you're inducing biological macromolecules to fill fibers to try and understand neurodegenerative disease, arthritis, and connective tissue. This used to be a much bigger part of our program 10 years ago, and then a few people retired, but these capabilities still exist. One other area that's will be affected by APSU will be fiber diffraction imaging. This is again a small part of our program, but we've had a couple interesting recent publications on college instruction and teeth, among other things, and a number of publications from the Oracle group. And so these have applications in neurodegenerative disease, arthritis, cancer metastasis, traumatic brain injury, connective tissue diseases. And so for doing these things, it's if you can get a preparation that's like a histology preparation that has fibrous proteins in them, then you can use this to find the amount in structure and orientation of these things. And that can be correlated with other imaging techniques to try and understand disease mechanisms. About 70% of our business is macromolecular small angle X-ray scattering. Most of this is equilibrium sacks. And so we're looking at structure macromolecules, either in complexes as an application, protein-ligand interactions, and flexible and intrinsic disordered proteins. So these are all strengths of sacks, and it's very highly complementary technique to other biophysical techniques, including cryo-electron microscopy. And a very small but important part of our program is time-resolved sacks, where it started off, we were looking at protein and RNA folding, but we're now expanding this much more into enzymatic kinetics. And so this is now a practical modality, and we're encouraging people to try and take this up. And the first publications are starting to come out in this new mode, where we can go from time regimes of around 100 microseconds up to several hundred microseconds, and then into the millisecond range, depending on the system. So that's what we do. So what's unique about us is we have the only muscle diffraction program in the US. And there's only 2 other beamlines worldwide where this is done routinely. And the axis has actually shrunk a little bit in recent since one beamline was taken on action in Japan, which was unfortunate. We feel we have the most advanced facility for equilibrium sacks in the US. It has a lot of other places of similar capability, but we've been doing it a little bit longer. And we have certainly had the strongest, most evolved time resolved microseconds to second SACS program worldwide. And so this is where we're unique, but we're comparable to many other facilities in the US and around the world in other respects. So what is APSU? The APS is now 30 years old, and it's like an aircraft carrier or something like that. Badly needs a refit. Things are wearing out. And so what they're doing is they sought funding from the Department of Energy to do an $800 million upgrade to build an entirely new accelerator in the existing building and storage ring. It's and completely replace it. It's a new design. A lot of the other larger facilities have undergone similar things, but there's this new design for technical among. It's called a multi-band achromat design. And what this allows them to do is to reduce what they call the electron beam emittance by a very large fraction, in this case, a factor of 70. So this is source size times divergence. So both divergence are going down, but there's a very large difference in the horizontal source size that will be important for us. They will just double the stored beam current, 200 milliamps, and this will provide most of the doubling in flux that we'll do. It's actually a little bit more than that. They give the exact numbers in. So anyway, the APSU project gave you all these inscrutable numbers, but the really important ones to look at are in this red box here. So look at the APS now, that the horizontal boom size is currently about 200 microns. And then we can see that there is two modes. The one that we're using most of the time with the brightness mode, and then this timing mode. So it's actually the horizontal beam size about a factor 20 smaller. And if you take a look at that, then it's much more comparable to the existing vertical beam size of around 10 microns, 15 and 13 over here. And the vertical beam size will be very much small in the vertical divergence. And so what this means then is that we have effectively a point source that's approximately round. And so this is much more convenient for focusing applications, and as we'll talk about later, will result in much better quality fiber diffraction patterns. It will no longer matter in which orientation you put the sample in the beam. So what this means for us, much smaller source size, vertical size and divergent, about a third, about what B, about the same in time mode. But the horizontal size is 20 less, and the divergence about a quarter times this. And so what that means then, when we focus this with the beamline optics, our current focal plots a little bit smaller by 30 and 140 microns will go down to around 10 by 10 microns theoretically, and be limited by the aberrations and things. But since this is very much smaller than the pixel size in the detector, it'd be almost irrelevant in terms of analyzing our data. This is a big change. This will result in greatly improved data quality. And also means that even though the flux is down 2 or 3 times higher, the flux density is about 100-fold. And so, this is in flux per unit area. This improved signal noise in all experiments, and so better data. This also means more intensive or better time resolved experiments, and it's just going to be easier to get this kind of data. And again, the beam will be approximately symmetrical and much smaller than the pixel size on our detectors, much higher quality X-ray fiber diffraction patterns. Another interesting thing is we currently have to do time resolved SACS by introducing a compound refractive lens to focus a microbeam from these things. We'll no longer need to do this, most likely. We'll be able to do it with the main beamline optics, and this will allow us to switch back and forth from regular equilibrium SACS or even muscle experiments to the time resolved SACS experiments, making it much easier to do and to schedule. And that will lead to an overall rise in productivity. So these are all very good things. To the extent that we do the experiments after upgrade, we're going to have much smaller beams for microbeam diffraction and scattering. And so our existing compound refractive lenses will be able to take all the light from the beam because it'll all fit into the input aperture of these things. And so the 1.8 meter compound refractive lens we currently get is run by 4 by 24 microns, be down by less than 2 by 2. And if you want to use this for time resolved SACs, we can, and we can also use this in micro diffraction experiments. We also have a 50 centimeter focal length compound refracted lens, and the beam size will be less than a half a micron. Excuse me. In each direction. And so these will have interesting scientific opportunities. And so we've haven't done a lot of this up to date, but we have the ability to take, say, cryofrozen histology specimens, and you put them in the beam, you can scan them, take a picture at each spot, and build up an image to see how fibrous molecules are arranged. And this is an old one looking at a rat hippocampus and looking at the orientation of myelin as various spots, but indicate with these little arrows. The heat map in this particular case is indicating despacing in these things. So you can actually image any part of the pattern, either the total amount, and the orientation, and lattice spacing. Any of these things can be imaged and compared, and you can compare these to other imaging modalities to build up a picture of what you're looking at. And so after APSU, this could be a much better capability. Again, we don't do very much of this right now, but it's something to park in the back of your mind. It is something that we can do. So what's this going to do to our user program? Well, it's going to take a year to build the new accelerator. So it's shutting down on April 17th, 2023, and restarting operations beginning April 2024. And during this dark period, there will be no user access to the APS, and the accelerator will be being built, and there won't be any running. This schedule might slip a little bit, but what I've been told, if that the accelerator is ready to install on April 7th, 2023, they'll go down and start regardless. And that's probably in the best shape and is less vulnerable to supply chain issues and some of the beamline things. So this is probably likely to happen. So during that time, what we're going to be doing is doing refurbishments and improvements of beamline 18ID. And so what I want the rest of this meeting to do is Wei Kong will tell you about the benefits of APSU and the things we're going to be doing to improve muscle fiber experiments. That'll be followed by Jesse, who'll talk about the benefits and improvements of SACS experiments. And then I'm going to finish off to say how we plan to continue to serve the user community during the dark period, and mainly talking about how we're going to have some sort of access to the APS. So I'll stop there.